Hi, welcome to the Olympiad geometry. Let's continue our study. Before we start, if you think this video is helpful, please click the like button, comment, share, and subscribe to the channel. So let's continue our study on the Circumcenter property supplementary. Basically, these are several problems associated with the Circumcenter. Let's solve them together. The first one. A circle passing through the circumcenter and the vertex of a triangle intersect two sides from the vertex on points PQ. So let's draw the figure first. Okay, we draw the circle and we have the triangle ABC, and we want to find the circumcenter here. O, and we connect AO. Okay, so a circle passing through the circumcenter O and the vertex, we choose A, of the triangle ABC intersect two sides from the vertex, which is OA and OB, on points PQ. So we want to draw a circle that passing through the AO, right? And also intersect with AB and AC. So I'm trying to, it looks like this. Right, that's a circle. So we have this circle intersect AB and AC on PQ. Then the symmetrical point of the other intersection point, which is this point, right? So let's call it M. It's asking the symmetrical point of M to PQ. To PQ is on the third side of the triangle. So it's basically asking us to prove that the symmetrical point of M, let's call it M prime, right? M prime. So symmetrical point of M to PQ is on BC. Right, so the problem is that we have the triangle ABC, we have the circumcircle of the triangle ABC, and we have another circle that passing through O and A. This circle meets AB, AC on PQ respectively, meets the circumcircle of the triangle ABC on point M. And we want to prove that the symmetrical point of M to PQ is on BC, right? So when we get this problem, we just need to think about how can we relate all of the points together, right? Because this problem is definitely, we need to prove it based on the angles. So if you look at the angle MPA, right, the angle MPA, it equals to angle MOA, right? If I connect MP and I connect MO, we know that angle MPA equals to angle MOA. And it's obvious it equals to twice of angle MBA, right? Because in the circle O, angle MOA is twice of angle MBA. Right, equals to twice of angle MBA, twice of angle MBA. And the angle MPA equals to angle MBA plus angle BMP. So it equals to angle MBA plus angle BMP, which means angle MBA, right? Twice of A equals to this one. So we know that angle MBA equals to angle BMP, which means angle MBA equals to angle BMP. So BP equals to PM. We got PB equals to PM here. Now we can think of that. We want to prove that the symmetrical point of M to PQ is on BC. So once we find that point, then we know that MP definitely equals to PM prime, right? So let's just think about draw this circle first that is centered at P with a radius PB, right? So we can find circle P with radius PB. And this circle meets BC on point N, right? So basically, that is a point. Let's call this point as N. Now we want to prove that M and N are symmetrical to PQ. Which means here we already know, because N is on the circle centered with P and radius is PB. So we know that PN equals to PB equals to PM. Right? We already know that. Which means if we want to prove that N is a symmetrical, and this N is on BC, right? And now we want to prove that this point N is a symmetrical point of M to PQ. So the problem is equivalent to prove that angle MPQ equals to angle MPQ, right? So let's look at the angle MPN. The angle MPN equals to twice of angle MBN. Right, because MBN are on the circle with the center at P and PBP MPN as a radius, right? So the angle MPN equals twice of angle MBN, and that equals to twice of angle MBC, which equals to angle MOC, right? So twice of angle MBN, that is twice of angle MBC, which is angle MOC. So let's connect OC here. And we already know that angle MPQ equals to angle MOQ. Right, angle MPQ equals to angle MOQ. So what we know here is that angle MPN is angle MPN equals to angle MOC. Right, and also angle MPQ equals to angle MOQ. So this angle equals to this one equals to this one. In other words, if we can prove angle QOC equals to angle MOQ, then we prove that angle MPQ equals to angle MPQ, right? Which means the problem is changed to prove angle MOQ equals to angle COQ, right? And look at the triangle MOQ and triangle COQ. Okay, so we connect MQ here. We know that angle OCQ equals to angle OAQ, right? Because OC equals to OA, so angle OCQ equals to angle OAQ. And angle OAQ equals to angle OMQ. So this angle equals to this one. And angle OQC, angle OQC let me see, yeah, and so angle OQC, this one, equals to angle OMA, right? Because MOQA are cyclic, so angle OQC equals to angle OMA. And angle MQC, MQO, or OQM, right? That's right. Angle OQM. Angle OQM equals to angle OAM. Right? Angle OQM equals to angle OAM because they all reference to the chord MO. Which means we know that angle OAM equals to angle OMA. Right, because OA and OM are the radius of the circumcircle of the triangle ABC. So these two angles are equal, which means we get that angle OQC equals to angle OQM. Now we know that angle OQC equals to angle OQM. So in the triangle OQC and the triangle OQM, we know that angle OQC equals to angle OQM and angle OCQ equals to angle OMQ, which means angle QOC equals to angle QOM, right? Angle QOC equals to angle QOM, and we know angle QOM equals to angle QPM, right? And angle QOC equals to angle QOM, that is half of angle MOC, which is half of angle MPN, right? And which means we get that angle QPM is half of angle MPN, which means angle MPQ equals to angle MPQ, right? So we have angle MPQ equals to angle MPQ. Then we know that PM equals to PN, PQ equals to PQ, and angle MPQ equals to angle MPQ, which means triangle MPQ and triangle MPQ are congruent, right? And it's easy to know that M and N are symmetrical points. Therefore, the symmetrical point of M to PQ is on BC. Okay, that's let's call it problem one. It's property one as well. So let's see the second one. Okay. The second one. Let Let O be the circumcenter of triangle ABC. Circumcircle of triangle ABO meets AC on X. Circumcircle of triangle ACO meets line AB on Y. Then OXY are collinear and the line OXY is perpendicular to line BC. So let's draw the figure first. And we have the circumcenter here. This is O, and we want to find the circumcircle of triangle ABO. Roughly say the center is here. So we have a circle look like this, right? And this ABO meets AC. Let's draw it like this. Meets AC on this point. Let's call it X, right? And the circumcircle of triangle ACO. Circumcircle of the triangle ACO, which is, I'm trying to find the center, right? So that's a circumcircle of the triangle AOC meets AB on Y. Right? Then we want to prove that X, Y, O are collinear and OXY is perpendicular to line BC. So this problem is a little tricky, right? Just because we don't really need to prove that X, Y, O are collinear. Because we just need to prove either XO or YO is perpendicular to BC. Right? Because O is a circumcenter of the triangle ABC. So if YO is perpendicular to BC, that means YO is a perpendicular bisector of BC, and the perpendicular bisector of BC is only one line, right? So we may have other lines that can be perpendicular to BC, but the perpendicular bisector is only one line. And we can directly use the methods that we prove YO is perpendicular to BC. We can prove that XO is perpendicular to BC. And then we know that because YO is perpendicular to BC and it's a perpendicular bisector of BC, so XO must be the perpendicular bisector of BC as well, which means XYO are on the same line. So XYO are collinear. Okay, now the problem is easy. We just need to prove that YO is perpendicular to BC. Right, we just need to prove YO is perpendicular to BC. Now think about what we have here. How we get the point Y. We basically find the circumcircle of the triangle AOC here. Right, we find the circumcircle of the triangle AOC, and that circle meets AB on a point Y. So we want to prove that this point is perpendicular to BC. Then we can connect YO and extend it, meet BC on a point, let's call it M. Right, So what is angle BYM? Angle BYM equals to angle ACO, right? Which equals to half of 180 minus twice of angle B, which equals to 90 degree minus angle B. Right, that's angle BYM. So angle YMB equals to 180 degree minus angle B minus angle BYM, which is this one. So it equals to 90 degree, which means YM is perpendicular to BC. And we know M must be the midpoint of BC, right? So similar, we can do the proof for the X point. Then X, Y, O are collinear. Okay, let's move on to the next one. A circle passing through the circumcenter O and one vertex of a triangle intersects two sides with a vertex on point DF. So this figure is identical to the figure of the first problem, right? So let's just draw it first. It seems that a circle passing through the circumcenter O and one vertex of triangle, so here, and intersect two sides with a vertex, that's AB and AC, on point D and F. So it's just a different name of the points now. Let me try to do the plot. Right, this roughly say is our plot. So here is point D, here is point F. Then orthocenter of ODF, orthocenter of the triangle ODF. We want to find the orthocenter of the triangle ODF. It's saying we want to prove that orthocenter of the triangle ODF is on the opposite side of the vertex, which means we want to prove that orthocenter of triangle ODF is on BC. Right. Prove orthocenter of triangle ODF is on BC. So to prove this one, I want to remind the audience that we proved one problem before, which is Miko's point. Right, if you remember that we find the triangle ABC and we find three arbitrary points on the BC, CA, AB. So we have A prime, B prime, and C prime. So if we find the circle of the triangle A, B prime, C prime, probably it looks like this, right? And we find the circumcircle of the triangle B, A prime, C prime. So it looks like this. Then these two circle intersect on a point, let's call it M. And then this M is on the circumcircle of the triangle CB prime A prime. We can quickly prove this again. So if we connect C prime M, connect A prime M, and connect B prime M, then we know that angle B prime M C prime equals to 180 degree minus angle A, and angle C prime M B, no, C prime M A prime, C prime M A prime equals to 180 degree minus angle B, which means angle B prime M A prime equals to 360 minus angle, minus this one, so minus 180 plus angle A minus 180 plus angle B equals to angle A plus angle B. Right, that's angle B prime M A prime, which means angle B prime M A prime plus angle C equals to 180 degree. So B prime M A prime C are cyclic. Right? Now for this problem, we already have a circle here. Then we can just find the circumcircle of the triangle DBO. Let's call it, and the circumcircle of the triangle DBO. Meets BC on another point, let's call it E. Right? So we know that based on the Miko point, we know that now O is the Miko's point of triangle ABC. Right? Because when we find the circumcircle of the triangle BDO meets the point E here, then we know that angle DOF is 180 degree minus angle A, and angle DOE is 180 degree minus angle B. So the angle FOE is 180 degree minus angle C, which means FOEC are cyclic, which means O is a Miko's point of the triangle ABC. Right? Then the question is, if we connect DE and if we connect FE. Remember that we want to prove orthocenter of the triangle DOF is on BC. So if we can prove O is orthocenter of the triangle EDF, then we prove that E is orthocenter of the triangle DOF, and also it's on the side BC, right? So can we prove O is the orthocenter of triangle DEF? Right? To prove that, we just need to extend the OE to a point. Let's call it P here. Then we can think of the angle DEO equals to angle DBO, right? Angle DEO equals to angle DBO, which is half of 180 minus twice of angle C, right? Because angle BOA is twice of angle C. So it equals to 90 degree minus angle C. That's the angle DEO. And for the angle EDF, the angle EDF equals to angle EDO plus angle FDO, which equals to angle EBO plus angle FAO, which equals to the angle EBO is half of 180 minus angle twice of angle A, right? And plus the angle FAO. FAO is half of 180 degree minus twice of angle B. So it equals to 180 degree minus angle A minus angle B equals to angle C. Which means the angle DEO or angle DEP, the angle DEO plus angle EDF equals to 90 degree, which means EO is perpendicular to DF. So for OF and DO, we can use a similar way to prove that. Then we know that O is the orthocenter of the triangle DEF, which means E is the orthocenter of triangle DOF. This is an orthocenter group. Okay, that's for the problem 3. And we have the conclusion. Conclusion is saying that in the triangle ABC, M is a circumcenter while being the midpoint of the triangle ABC. Then the orthocenter of the midpoint triangle is a point M, right? So basically it's just replace the O to M. O is a orthocenter of the triangle. O is a circumcenter of the triangle ABC while it's a midpoint of the triangle ABC. Then the orthocenter of the midpoint triangle, which is a triangle DEF. The orthocenter of the triangle DEF is a it is a point M, which is O here, right? So that's obvious. Okay, let's see the fourth problem, which also the property 4. Okay. Let O be the circumcenter of the triangle ABC. M is a midpoint of arc BAC. So we have the triangle ABC here. And we know that M is a midpoint of arc BAC. So we have the circumcenter O here, then the M must be on the perpendicular bisector of BC, right? So M is here. The circumcircle of triangle OAM. The circumcircle of the triangle OAM, which is which looks like this, right? That's a circumcircle of the triangle OAM. Intersect ABAC on EF. So this is E, this is F, respectively. Also intersect MB, MC on PQ. So this is MB, and this is MC on point P and point Q. Right. Then we want to prove that EB equals to EM, FC equals to FM, ME equals to MF, MP equals to CQ. We want to prove this. Let's look at the figure. This is a circumcenter O, so we know that AO equals to BO and equals to OC, right? What we have here is that M is a midpoint of the arc BAC. M is a midpoint of arc BAC, which means MB equals to MC, right? MB equals to MC. And we know that this circumcircle meets AB on E, meets AC on F, and meets MB on P, meets MC on Q. So we want to prove that EB equals to EM. Let's connect EM here. To prove EB equals to EM, we just need to prove angle EBM equals to angle EMB, right? We just need to prove this angle equals to this angle. And because OB equals to OM, so we know that angle OBM equals to angle OMB, which means we just need to prove that angle OBE equals to angle OME, which is obvious, right? Because angle OBE equals to angle OAE, and angle OAE equals to angle OME. So EM equals to BE. And for the FC and FM, they're the same, right? They're the same. FC and FM, just because we want to prove angle FC equals to FM, we need to prove angle FMC equals to angle FCM. And we already know that angle OMC equals to angle OCM. So if we can prove angle OCF equals to angle OMF, then we're done, right? And angle OCF equals to angle OAF, which equals to angle OMF. So it's true. And we want to prove that ME equals to MF. ME equals to MF. So if you look at the triangle MB and the triangle MCF, the MB equals to MF, MB equals to MC, right? MB equals to MC. And the angle EMB equals to, so the angle EMB equals to angle EBM, which is, if we think about it like this way, the angle EBM plus angle ABC equals to angle MCB. Right, and angle MCB plus angle MCF equals to angle ACB. I think we will use that later. So actually, if we want to prove ME equals to MF, we can let's see. I think we can do things like this. Yeah, so the angle MEF equals to angle MQF. Right, equals to angle MQF here. Actually, angle MEF equals to angle MOF may be easier because angle MOF can be rewritten as angle MOA plus angle AOF. Am I circling here? Let me think. So we want to prove ME equals to MF. If we want to prove that ME equals to MF, we can prove angle MEF equals to angle MFE, right? It equals to prove angle MEF equals to angle MFE. And the angle MEF can be rewritten as this one plus this one. And this one, the angle A, and angle MFE can be rewritten to, yeah, I don't want to break it because it will make the the fact is that we want to prove this triangle is congruent to this triangle. So, oh, yeah, right down here. So, let's think about this. So, because angle MEF equals to angle, angle MEA equals to angle MFA, right? Angle MEA equals to angle MFA. Angle MEA equals to angle MFA. This one equals to this one, right? And because triangle MBE and triangle MCF are isosceles triangles, so the angle MBE equals to angle MCF. And we already know that BM equals to CF, which means the triangle MBE is congruent to triangle MCF, which means ME equals to MF, right? ME equals to MF. And we also want to prove that MP equals to CQ. We already know that this angle equals to this angle. And we know that ME equals to MF. So, and MF equals to FC. So basically we have this side equals to this side, right? The angle PME equals to angle FCQ, and ME equals to MF equals to FC. Right, we want to prove that triangle MPE is congruent to triangle CFQ. So we just need to find the angle. The angle QFC equals to angle, see, this angle equals to angle MEQ. No, this angle equals this one plus this one equals 2. So it equals to angle QEA, right? The angle QF, actually QFC can be equal to angle QMA. Yeah, that is angle QE. So it equals to angle QMA. And let's look for the relation between QMA and angle MEP. Right? We know that angle MEP equals to angle how to do that. Angle MEP equals to angle MFP, right? It doesn't help. Or MOP. Will MOP help? I don't think so, right? Let's think about that. QFC, this one, equals to angle, because we already have this side and this angle, so we want to prove that CQ equals to MP. We want to prove that these two triangles are congruent, which means we need to find the angle relation of the angle QFC, or actually angle FQC. Right, because angle MPE plus angle MPE plus angle MFE equals to 180 degree, and angle MEF equals to angle this one equals to this one, right? The angle MEF plus angle MAF equals to 180 degree, right? Angle MEF plus angle MAF equals to 180 degree, and angle FQC equals to angle MAF, right? This one FQC equals to angle MAF, which means angle FQC plus angle MEF equals to 180 degree. Look at these two. So we know that because ME equals to MF, so angle MFE equals to angle MEF, which means angle MPE equals to angle FQC, right? That means that these two triangles are similar and the relative side are equal, which means these two triangles are congruent, which means MP equals to CQ. So okay, so the next one, if PQ satisfying MP equals to CQ, then MPQO are cyclic. Okay. It's basically saying that in the triangle, actually if we have the circumcircle here, we have a triangle ABC here. We know the midpoint of the arc BAC M here. and we know the auxiliary center O here, right? If we connect MB, connect MC, and we find a point that MP equals to CQ, right? MP equals to CQ. MP equals to CQ. Then we want to prove that MPOQ are cyclic. So this problem is actually easy to prove just because we can connect MO, and we know that angle BMO equals to angle CMO, right? This one equals to this one. And we know that MP equals to CQ. So consider about that P and Q are moving from MP and CM in the same speed, right? That keeps MP equals to CQ, right? So P starts moving from point M to B, and Q starts moving from point C to M in the same speed, because BM equals to CM. So we know that MP always equals to CQ. Then we can think about how can we get this condition that MP equals to CQ, right? If we find the perpendicular from O to MC and MB, let's call this point as K, this point as L. Then we know that the triangle MLO and the triangle MKO are congruent, right? Because this MO is the angle bisector of angle MBC. So ML equals to MK, right? ML equals to MK. Now, if we look at the triangle COK and triangle MLO, these two triangles are congruent too, right? Because the triangle OCK is congruent to triangle OMK. So these two triangles are congruent. And we know that CQ equals to MP. OM equals to OC. So OM equals to OC and CQ equals to MP, and angle PMO equals to angle OCQ, right? OCQ, which means triangle MPO is congruent to triangle CQO, right? Which means OP equals to OQ. Okay. OP equals to OQ. And also angle QOC equals to angle MOP, right? This angle equals to this angle. That means this angle equals to this one. The angle QOK equals to angle POL, right? Which means the angle POQ, equals to angle LOK, equals to 180 degree minus angle LMK, which means POQM are cyclic. Okay, in this video we discussed about several problems related to the Circumcenter. I don't think we can really use it as a property because these are kind of complex as a property, right? But I think it's a good practice we relate it as a problem for the Circumcenter. Okay, I hope you like this video. See you in next one. Thank you.